All right, we should have our note packets out, and we are on types of lenses. We are also going to have our ray diagram sheet, and we should have our 3 colored pencils and our ruler, because we're going to do some diagramming as we go through these notes today, okay? So, there are 2 basic types of lenses, just like there were 2 basic types of mirrors, okay? There's a converging lens, just like there was a converging mirror, and that brings the light together. That's important to understand. Now, a converging lens is actually going to be shaped as convex. That's going to be different from our mirrors, but everything else about it's the same. A diverging lens is going to spread the light out, okay? And that is the same as our mirror did, that spread the light out when it was a diverging mirror. Now, the shape of a diverging lens is a concave lens, which is opposite of our mirror, diverging mirror. Okay, so you need to understand that the converging part of it is all the same, and the diverging part of it is all the same, regardless of whether it's a lens or whether it's a mirror, but their shapes are different. Okay, that's the main thing. And that's why I really do talk about lenses more as converging and diverging versus their shape, because I know that gets a little bit confusing as we go along. All right. So a converging lens, which is convex, is much like a converging mirror, where the lens is going to take the light rays from infinity and converge them to a specific point called the focal point. The difference here is that the lens doesn't have a center of curvature. Rather, it's going to have a focal point on each side of the lens. So regardless of how light went through the lens, there would be a focal point. So we're not going to have that center of curvature like we did with the mirrors, but we'll have focal points on both sides. So, and that, like I said, is because of the fact that light can come from the left or it could come from the right. Regardless, they're going to come in and converge at that focal point. Now, the other thing I want you to know about refraction through lenses is light is always going to refract towards the thickest part of the lens. Since this is a convex lens, it's actually thicker in the middle than it is on the edges. So, as light rays come in, they're always going to bend towards this middle. Well, the bending towards the middle always makes them come to that focal point. Okay, so that's going to be huge. Obviously, converging lenses play an important role in our lives, as all of you have these types of lenses in your eyeballs. Oftentimes, we need additional corrective lenses to fix our vision, though, and that is because of the convergence not happening fast enough or correctly. Believe it or not, actually, the light gets bent twice in our eyes. It gets bent on your cornea, which is the clear covering right here, this part of the eye, okay, and it gets bent at the lens, okay. Now, excuse me, the A is the correct part. The retina is the screen on the back of your eye. So really, believe it or not, everybody, believes that your pupil is black. Your pupil is not really black. The reason you see it as black is the inner lining of your eyeball is black. And that's because it has photoreceptors that absorb all the light. And so that's why it is black, because that's what absorbs, and it doesn't reflect, because that's why you don't see colors. It's because what you see when you see colors is what's reflected and not absorbed. So all of the inside of your eye is black. Now, there is a specific spot where your nerve attaches to your eyeball, And when your nerve attaches to your eyeball, that's actually where your optic nerve attaches, is where your blind spot is. So if you hold your fingers in front of your eyes right now and you move them out towards your ears, okay, there'll be a spot where you'll like lose sight of them. That's because the image is forming on your retina right where your optic nerve is attached. There's no photoreceptors there, so you can't see it, and that's why everybody has a blind spot, okay? Now figure B, this eye doesn't allow the light to come together quick enough, okay? There's two reasons this happens. It's either that your eyeball is too short, you got a squatty little eyeball, or it has to do with the fact that your lens doesn't change shape quick enough as well. So that would be the other thing, is it's too thick. And so, actually, no, it's too thin. Yeah, it stays too thin. So there's several reasons why that happens, but what it is it ends up being that someone is far-sighted. So what we have to do is we put another converging lens in front of their eye to bring the light together quicker for them, and so that's why they wear corrective lenses. In figure C, your eyeball brings the light together too soon. Lots of times this is because your eyeball's a little more oblong, and so you've got a longer eyeball, or your lens is too thick and it brings it together too quickly. So on this one, you'll actually put a concave lens in front of your eye, and that will cause it to spread the light out a little more before your lens brings it together, so that will help correct it. So it's all about getting it to form on the screen properly. So that's the whole point of why we even worry about lenses, and why it's important to understand lenses, because most of us wear some sort of corrective lens at this point in time in our lives. If not, you will eventually, probably, with as much screen time as everybody has. Okay? Now your lens also changes shape. I want you to realize that. Your lens is attached to muscles, and your muscles pull it and stretch it thinner or thicker, depending on if you're looking at something further away or whether you're looking at something close, so that you can focus in on different things. When you look at your paper and then you look up at my screen, your eye has to change the focal length of your lens. So it has to change its thickness so that you can focus in on both of them. When you're really tired lots of times, sometimes that won't happen as fast, and you'll notice that everything will be a little bit more it'll be blurry when you first look up. And so that's sometimes just your eyeball not moving fast enough to make that happen. So that was a lot of information there. Didn't have to have it all written down, but I think it's really important that we talk about it. So a camera uses lenses as well. Some of y'all use cameras quite a bit to focus an image on photographic film. The film is exactly like your retina. You have to make sure that you get the right focal lengths between your lens and your film. Otherwise, you end up with a blurry picture. And again, it could be that you make it come together too early and it'll be blurry, or it'll be too late and it'll be blurry. So you have to get that just right so that it'll all converge in the right spot. Okay, so we're going to do ray diagrams, and this would be our ray diagram 101. Okay, again, we have 3 different rays. Now, the first ray is going to be drawn parallel again, and it's going to be drawn, it's going to refract through what I call the primary focal point. The primary focal point is where the light would go once it gets on this side. So if the light goes through, where's the thicker part? The thicker is in the middle. So this one would refract downward, so this is going to become my primary focal point right over here. If it was thicker on the outside, it would refract up, and then this one would become my primary focal point. So it depends on, again, the shape of the lens, which one's your primary focal point, okay? But rule 1 is that we draw it parallel in, and then it's going to refract to the thickest part of the lens, which on this one is in the middle, and it's going to go through the focal point in that direction. So this one will look like this. All right. Rule 2, you're going to draw a ray starting from the top of the object, but you're going to go through the secondary focal point, and then it's going to come out parallel on the other side after it refracts. So it's almost like if the light came the opposite direction, what would it do? So it'll go through this focal point, and then it'll refract out parallel. Whereas if we just turn those arrows opposite direction, it would look exactly like ray 1. Okay, that's the way to kind of think about it. Again, you only have to get 2 of these to intersect to get an image, all right? But the third one, in my opinion, is always the easiest, and it's drawn through the exact optic center of the lens. Okay, so the exact optic center is considered the origin, whereas if we shined light straight on there, it would go straight through. And that's how we create a principal axis and figure out where the center of a lens is we shine light straight at it so that it'll go straight through. We'll do this in a lab, okay? But you should have 3 rays. Notice what happens to all 3 of the refracted rays on the opposite side of the lens, because remember, the light wants to go to the other side. That's where it's supposed to be. So where with mirrors, we said if the image was on the same side, it was positive. With lenses, if the image is on the opposite side, now the opposite side is positive. Okay, we'll always say that this object distance is positive, but if the image is over here on this opposite side, that's going to be positive as well. Because we, again, where's the light supposed to go? And with a lens, it's supposed to go through. Excuse me. As before, so you draw the image down to the intersection as shown. So here's our image. Since this image could be projected on a screen, it's considered to be a real image, and real images are always found on the opposite side of the lens from the object. Likewise, virtual images should appear on the same side as the object. So it's a little bit different than mirrors. But the characteristics are still that we can say it's inverted, it's upright, it's reduced, the same size, or magnified. All those things still apply. This one is reduced, and it is inverted. I will also remind you, inverted and real always go together, and virtual and upright always go together. So those are things that you can definitely always key in on also. So now we're ray diagramming it, so now get your colored pencils. If we need to take a break and make sure everybody gets their colored pencils and has their rulers, then do it now. All right? You can hit pause on this and everybody can be ready to go. Get out your case diagrams, your ray diagrams for lenses, and let's draw. So first one, in parallel, the thicker part of the lens is in the middle, so it's going to refract down through the focal point. Okay, the second one would go through the secondary focal point and then across. Oh, let me do that. I'll draw it with my black one. I'm not sure I do it on this one. Let me see. Oh, I don't. Okay. So I will say I always draw 3 before I draw 2 because it's easier, but I'll go ahead and put it on here since this is our first one. So we'll go from our tip of our object through our focal point, hit the lens, and then we will go out parallel. I hope I draw a pretty good line here. And I have an arrow there because that's coming in, and I have an arrow there because it's going out. And then I did my center of... Oh, good, I did good. There we go. All right, so they all intersect in about the same spot. And there's our image, and we need to do our characteristics. It is on the opposing side, which means that it is real, it is inverted, and if we measure this height compared to that height, it is inverted. So it's real, it's reduced, it's inverted, it's located between the 2 and F and the F. You don't have to write that part of it, but that's just some extra information there. All right, let's keep going. All right, first one, in parallel, thicker part of the lens is in the middle, so it refracts down. I go to the third one goes through the center of curvature, or the center of the optic center of my lens, not the center of curvature. So then it forms right there. Notice when it's a 2F, it's a 2F. It's very similar to our mirror when it was almost at the center of curvature, because remember the center of curvature was 2F. So there's some similarities going on here that you should realize. It's real, it's the same size, it's inverted, located at the same location on the opposite side of the lens. Okay, in parallel, out through the focal, which is going to make it go down. I don't know why I changed colors. I just did. Sorry. Then I could still do ray 2. It can go through the focal point, hit the lens, come out parallel. I don't draw it though. I do ray 3. They intersect there, which gives me an image here. So it is real, it's inverted, and it's magnified or larger, whichever one you want to say. All right. And it is located further and further away from the lens. If you go back to your mirror ray diagrams, you're going to notice that happened too. Oh, look, it's the end of the school day. So there's our bell. All right, case 4, we're at the focal point. So it goes in, and it's going to refract down through my focal point, my primary focal point, which is at the thicker part of the lens. Then my secondary one, oh, those are going to be parallel to each other. So guess what? No image. Wow, just like our mirrors. It's pretty cool. Okay, so you're going to notice a trend going on. Okay. All right, so we're at case 5. The object is now between the F and the focal and the lens. Okay, I'm going to erase this little part right here, so we'll see that in a minute. So this time, we're going to go in parallel, and then we're going to go out through the focal. So remember, it's thickest in the middle, so it's going to refract down. I want you to extend this line, though, backwards. And I want you to make it dashed. Okay, because the light's not supposed to be on that side, remember, so that's why it's dashed. Then I'm going to do my center of curve, through my center, optic center. I will say this line right here can be solid or it can be dashed. I kind of prefer it to be dashed above it. So only from here forward should it be a solid line, but then it can be dashed. So I have my intersection. On this one, we cannot draw number 2, so that isn't worried about it all anyway. But we've got an intersection of 2 lines, so our image would be over here. Oh my gosh, what happened? It went right side up. Oh, that would make it virtual. The other thing is notice it's on the same side as the actual object. It's upright and it's magnified. Okay, so those are all important things to write down on your cases. All right, so now we're going to change the type of lens we're dealing with here. It looks like I left my ray 2 on here. I'll erase it and redraw it though so y'all can see it. Okay, so I have my first one is going to go in parallel, but you need to think, where's the thicker part of the lens? That's where the light's going to refract to. And because the thicker part of the lens is on the edges, it's going to refract upwards, which means it's going to go like that. And then I want you to, that is actually lined up with your focal point that's in the negative zone is what I call it. So this becomes the primary focal point for this one. So that's just kind of one of those thought processes. We have to go through this focal point instead. Now, the second ray is a little bit different to draw. So you line up the tip of your object and the positive focal point as the light comes in. So it's going to be like this because I've lined it up. Then it's going to refract and it's going to go out parallel. Let me see my principal axis there. And it goes out parallel. Okay. Now I'm going to extend this refracted line backwards though. Okay, as a dashed line. That's not super pretty, but that's okay. And then I'm going to go through my optic center of my lens. And they should intersect. And I actually was a little high on that one. That's why. That's why I don't like drawing this line. Okay. So I draw it coming in. and then I draw it coming out, and then draw it going backwards. That's much better. I like that one better. That's much better. Okay. So, again, I like to draw array 2. I prefer 1 and 3, but that's okay. I've got an intersection. That intersection is there. Guess what? It's virtual, it's reduced, and it's upright. And this is the only type of image it makes. Very much like our diverging mirror only made one type of image too. I know it's crazy how much the similarities are, guys. All right. So here's another one. Let's see if we can figure it out. It goes in parallel. It's going to refract to the thicker part, which is on the outside, so that's going to go up. We draw that angle through the primary focal point as a dashed line, and then we go through the geometric center of my lens, and so those are right there. This one's also virtual, it's also reduced, and it's also upright. Okay. Hopefully this makes sense. Hopefully you're understanding. Help each other out. Remember, we can go back through this if you need to. What if there are two lenses? Oh my gosh. Really what you do is you make an image with one lens, and that image becomes your object for your second lens. So we'll start here, and we'll go in parallel. We'll refract through our primary focal point. Then we'll go through our geometric center of our lens, and we have our intersection. We will then make our first image. Our first image becomes our object of our second one. So we'll go parallel in, which yet my lens isn't wide enough on my picture, but it makes sense. Okay, but the thicker part is on the edge, so it's going to refract out. Okay, and then I'm going to go through the geometric center of my lens, and then those intersected right there. So my actual image is smaller, inverted, and real, because we are comparing it to my first original object. So because it's inverted, it is considered to be real, and we would actually be able to put this on a projection screen. I won't ever give you more than one lens like this, but this is how glasses work lots of times, so that's kind of the thought process, but it would be that the object is more over here instead, because the convex lens or the converging lens is like our eyeball lens. So I like for y'all just to be able to see how to do it. Oh my gosh, this looks exactly like the same one we've already done. It's crazy. Yeah, the formulas are exactly the same. So we can work on these, but the only thing to realize is your DO is always going to be positive. Your DI is positive if it's on the opposite side of the lens, and your focal lengths are positive if they're on the opposite side of the lens. So this is a converging lens, so that means the focal length is going to be a positive value. So that's kind of one of those things to think about. Converging lenses are those focal points that the primary focal points on the opposite side of where our image or our object is. So we could do our math. We do our inverse. So 1 over 20 minus 1 over 35. Take the inverse and you should come up with 46.7 centimeters. We can figure out the magnification by doing our negative DI over DO, which should then come up with 1.33 negative. Okay, so because it's negative, that means it would be real. Because it's 1.33, that would mean that it is larger, and it is inverted because it's negative. Also because it's real. Oh, sorry, I hit the mic. All right, gang, you have stuff you can continue to work on in class, and you have worksheets. Work on those for the rest of the time, and have a great day.